So I'm now going to talk to you this morning about the fingerprint of intelligence. I rather like that title because in my view, I'm quite unashamed, God has left his fingerprint on creation. He's left us with every reason to believe that he's there. But I'm not going to assume the Bible, which I do believe in. I'm going to come in from the science and to show you that on the basis of thermodynamics and information, we have to accept the statement that I've just made, that there is a fingerprint of intelligence in the world. That is a transcendent intelligence. As I say, I'm not assuming the Bible in this talk, but it will come in as I come back to the main thesis of what I'm saying, which is that God has left his fingerprint on the world. Let me make some introductory remarks first. Now, some people may be aware of William Dembski's work. He's the author of the website Uncommon Descent. He wouldn't actually agree with me on a young earth position, but he would nevertheless say that there is definitely intelligence which has acted in the world, and therefore we cannot say that everything came about by evolutionary processes. If you see a lava lamp with 22 on, you know that that could either be a fluke or else there's information, particularly if it went to 23, 24, and so on. You would immediately perceive that that cannot be natural law. And William Dembski has made that point very ably in his various books. One of them's called No Free Lunch, and there's quite a number of others that he has written. So if I see a lava lamp doing that, I know that that cannot be natural law. That's an obvious point. I'm really appealing to your intuition here. I'm not particularly proving that. I'm just saying this is my experience. We know, we can observe, we can perceive when something is actually involving something other than just gravity or some flow of some natural law. If we see a lava lamp do that, we know that can't be a natural law. Another point is this, that rolling a dice increases the number of possibilities, and this increases the likelihood of different sequences. That's obvious. But you're not going to get this type of wording, are you? You're not going to get this type of phrase, time and tide wait for no man, in a Scrabble board, or you're not going to get a whole series of sixes, back to the dice, usually. It's going to, if you were to get that, then it would be more than chance. It would be a dice. And on the Scrabble board, if I got that, you would know immediately that there is something other than chance going on. In other words, true information, whether it be a whole series of sixes or whether it be an ordered 6-3, 6-3, 6-3, something like that, is immediately telling you, hey, there's something other than natural law going on. In other words, there is a specific sequence, and the specific sequence suggests information, right? And this is a particular sequence, but of course it requires one to understand the code, which in this case is English, right? So if a Chinese man saw that, he'd say, well, what's going on? So with all respect to those who wouldn't know English, but you know, there could be somebody else who doesn't understand English, and he wouldn't necessarily see that as a specific sequence. Well, that's a fairly intuitive point. So a lot of these things are fairly obvious to most of us. Information requires codes and language and a message. So if I start using a Scrabble board, in English, I can spell the word family, fun, home, laugh and play, right? And it requires codes, and a message is using those codes. Now, I'm going to attempt to come at this a little bit more rigorously in a moment, but that's the general area that I'm exploring in this talk. And some further point, hardware doesn't write software. You don't get hands coming out, or equivalent to hands, coming out from the computer writing the software which drives it. That's obviously nonsensical. And most of us realize this. You don't need a PhD in physics or computers and information, you don't need higher degrees to understand that point. A child can grasp that. He knows that intelligence must be required, even to code Dell computers and those with Windows XP. Just in a similar way, you could talk about the music is not defined by the musical score. The musical score is just a means of communication of this wonderful piece of Mendelssohn's violin concerto, but the music transcends that score. And so we know this intuitively. You don't really need me to tell you this point. Now, G.K. Chesterton was a very clever person in his day, and he argued very strongly against the materialism which has gripped the universities in the West today. He and C.S. Lewis were probably some of the greatest minds of their day in the period during the war and after the war. They knew each other, and there was really a strong sense that the academia were going wrong. Let me just take you through this quote. He said, "Take the first more obvious case of materialism. As an explanation of the world, materialism has a sort of insane simplicity. It has just the quality of a madman's argument. We have at once the sense of it covering everything and the sense of it leaving everything out. Contemplate some able and sincere materialist, and you may consider a gentleman from Oxford, or you may, that would be, of course, Richard Dawkins, or you may consider Steve Jones from London, who's another materialist, who argues that we're just we're just a bunch of neurons. Basically, Richard Dawkins thinks that his brain is just a lump of meat. That's what he said on one occasion to one of my friends. And you could think of Peter Atkins from Oxford, who very much is of this view. We call such people reductionists. So he says, contemplate some able and sincere materialist, and you will have exactly this unique sensation. He understands everything, at least he says that, and everything doesn't seem worth understanding. What's the point of it? You know? Okay, so we can reduce it to a lot of flying neurons, but we haven't really grasped the big picture. His cosmos, Chesterton says it very succinctly here, may be complete in every rivet and cogwheel, but still his cosmos is smaller than our world. Let me use one other illustration. Supposing I look at Monet's wonderful poppy field picture. You know the picture? Beautiful impressionist picture. Now, if I got very close, I could actually analyse all the brush strokes and say, yes, it's got this colour here, it's got that colour there, and I could describe everything in detail. But would I have understood Monet's poppy field? You wouldn't. You wouldn't have grasped it. You'd have to step back from that brilliant impressionist picture and say, wow, now I understand what he was getting at. I love that picture, by the way. I think it's actually one of the most beautiful impressionist pictures. Or think of Leonardo da Vinci's Mona Lisa, which has this sort of eerie quality about it as the lady's eyes follow you wherever you are in the room. It's this type of art which reductionism cannot explain, and it's true in the sciences as well. That's really what Chesterton is actually saying. So, a famous point was made to me on a radio program once where I was in discussion with Richard Dawkins, and he said that there's plenty of energy out there to build living systems from nothing. He put it slightly differently, but he basically was saying that when I posed to him that thermodynamically you can't build machinery, he said, oh, there's plenty of energy out there. All you need is just energy. Now, I'm going to show you that that is not the case. And that isn't all you need. I posed the rhetorical question, is that really all you need? Of course it isn't. We need something far more. The universe isn't just matter and energy. That's really the thesis of this talk. There's something far more. So I'm going to stretch your minds in this talk, and I make no apology for it, because people are trying to use sophisticated ideas and trying to blind us into thinking that there is no mind behind the universe, when even Einstein, who was not a Christian and who didn't agree with the particular position I would take, which is to believe in the Bible, but even the great Einstein understood that there had to be some mind behind the order and the harmony that he saw in the universe. And yet people claim to be going beyond even Einstein and say, there is nothing. There was nothing in the beginning, and nothing became everything. I don't believe that for a moment. I don't believe it's true biblically, obviously, but I also don't believe that it's good science. So we're going to look at devices and machines. We're then going to look at entropy, closed and open systems. Some of this you won't have come across before, but I guarantee that if you look at the literature, you've got to deal with those issues if you're going to argue and resist these points in the academia. Then I'm going to talk about molecular machines. I'm then going to talk about DNA and ATP, adenosine triphosphate. It's a special motor which is absolutely essential for building DNA. Then I'm going to talk about information using the ideas of thermodynamics, which I'll have laid down before that, and then I will conclude. We need to have some definitions. I'm going to define something in this talk. Now, you may have heard the words machine used in a different sense, but it's close to our intuitive understanding of machine, but I am making a very strict definition here. A machine, I'm going to say, is a device which captures or holds energy for converting it to work with measurable regularity. We call this, and I will bring out the definition of free energy a little bit later, but we call this a free energy device. Actually, intuitively, you can see that it involves having energy free to do something, right? So I'm going to say a machine then is a device which can either capture or hold the energy for converting it to work with measurable regularity. That means that not every device in this definition is a machine. A chair, for instance, is very useful for sitting down on, and I see some of you are using them to great effect. But according to this talk, and for my purposes here, a chair is not a machine, because a chair isn't using energy in that sense. It's stopping you from using excess energy, but it's not really actually a machine in the way that I'm referring to it. But an ejector seat, supposing you were in a fighter jet at 35,000 feet and things started going wrong, you'd be very pleased that it used energy to get you straight out of the plane and down you come eventually on a parachute. So that is a machine, according to my definitions here. So the difference between a machine and a device. A tornado is not a machine for a different reason this time. Since although it's got energy, it is a mechanism which is dissipating energy from the weather. It's not a machine because it doesn't do it with a regular outcome. So I wouldn't ask a tornado to stir my tea in the morning. Or to put it a little bit more realistically, but it still wouldn't work, I wouldn't ask a tornado, please come by and, give me a bit of wind energy, to blow on something, because it's not going to work, because I cannot predict it. It hasn't got a predictable outcome. I cannot use it in that sense. Although we can constrain the weather if we get a reasonably constant wind using a wind turbine, because it can then convert the energy from the wind into something useful. So that is a machine. So a tornado is not a machine, but a wind turbine is a machine as it converts energy with regularity. Sometimes I speak on the feather, and the feather has a remarkable sliding mechanism right down at the microscopic level. When the barbules coming off the barbs, the barbules going in one direction have hooks, the barbules going in the other direction have ridges, and so you get this sliding mechanism on a feather. It's very useful and very important, but for the purposes of my talk here, that is not, although it is a designed device, and I would argue for that strongly, it's not a machine in the definition that I'm using. Whereas photosynthesis, whereas the sun's rays come on a leaf, and there is a remarkable biochemistry mechanism here, it converts the energy from the sun, and it converts it such that it produces sugar and oxygen, which is very important, of course, for us. So that's why we need the plants doing what they're doing. Converts the carbon dioxide, and it converts it into sugar and oxygen. But that is using energy. So it is a machine. Now I'm going to do some thermodynamics for you. Is this you? The more I think, the more confused I get. I rather like that picture because I think it summarizes, if we're honest, most of us. We easily get confused. This poor little chappie looks very confused. I hope that's not going to be you by the end of this talk. I've got an equation for you here. I said there would be some. The first law of thermodynamics. The total amount of energy in a given system is conserved. Energy is neither created nor destroyed. So basically this is saying that you've got work done and you've got heat, but the amount of energy in the system is always, the total of it is always going to be the same. Surprisingly, it took a long while before people got to grasp that point. And it wasn't until the 19th century that a few well-known thermodynamicists, people like Joule from Manchester, and other people, also like Carnot, and famous thermodynamicists like that, began to actually formulate laws of thermodynamics, and this was the first law. That one we're not going to major on, but it is important to know it. The second law, and there are actually 4 laws in all, I'm not going to mention the third law and the 0th law, I'll just pass over them, but the third law is to do with a zero of temperature, and the 0th law is to do with actually one they thought of afterwards, which is why the 0 is there, to say, oh, well, it really should come before the first. It is to do with the equilibrium of one system with 2 others, and those 2 others are in equilibrium if they individually are in equilibrium with that first system. We're not going to need that, and I'm not going to dwell on it. It's really the second law which is the issue. In an isolated system, the amount of energy that cannot be used to do work is always increasing. In other words, there's always waste. That's basically what it's saying. But this, we must acknowledge, as it's formulated here, is in an isolated system. That is, you've got nothing going in and out of the boundary round this system, whatever it might be. So we call the energy lost per degree a term which often confuses people, and it's called entropy. Entropy is like wasted energy, but we have to talk about wasted energy per unit of temperature. So it's got the units of energy per degree. But loosely, you can say that it's the wasted energy which is not going to be able to do anything useful again, right? Any process whereby you do some work will waste some energy to heat, and it will just dissipate. And it's lost, chaps. You're not going to get it back. Now, that has big implications for the universe if we call that an isolated system, and most people would regard that as isolated, although there's some rather surrealistic astrophysics going on these days where people try to argue for a multiverse, right? And they say there's lots of universes, and then I suppose we have to say that the universe is no longer an isolated system, and they appeal, as I say, in really surrealistic ideas, saying, oh, well, maybe there's a universe out there, and there's lots of universes, and we'll happen to be one of them that just so happens to have got everything right. That sort of reasoning. Well, I'm not going down that line tonight. Most of us actually would acknowledge that that is rather foolish type of appeal to something you can't prove. So we'll just stick with the universe, and we'll say that the universe is an isolated system. And so what it does mean is that the universe is essentially running down. It's actually dissipating energy as it goes on. So even though I don't accept the traditional Big Bang model, let me make this point, that when people propose the idea of a Big Bang, and it's not my view, I don't think that this is what happened, but when they proposed that, it had a big implication in those days when it was proposed, because it meant that there was a beginning. Even though I don't accept their view of the beginning, at least it made them realize that there had to be a beginning and that the universe was winding down from it, and nobody liked this idea of a beginning. And they began to say, oh, well, you know, that means that there has to be somebody who started it off, who lit the blue touch paper and made the Big Bang. Actually, it's not a Big Bang in 3 dimensions, it's a Big Bang in their idea of 4 dimensions, which is very difficult for us to understand. And I don't particularly want to discuss that in depth here. Suffice to say that they say that wherever you look, there was no particular preferred spot in the universe where things were being stretched from. And that's why I don't accept it, because actually I think all the indications are that there is a natural point from which everything in 3 dimensions, not 4, is expanding from. That's, by the way, to my main point here, because I actually want to discuss the laws of thermodynamics. The only reason I mentioned it there is that it has an implication that there has to be a beginning. And nobody liked this idea that there has to be a beginning. And of course that's why lots of astrophysics has been done since, trying to argue that actually nothing could produce the whole universe. Now, this law, though, has big implications, because as you can see here, there is the loss of useful energy. This aeroplane is actually a good and important machine. It's enabling this pilot to go forward, but he's losing energy. He's losing energy which is no longer able to do work. And we call that entropy, which is the amount of energy lost, as I said, per degree. And it's sometimes we would call it the disorganized energy, the energy which hasn't done anything useful and it is lost. Now, we come to non-isolated systems, and this is where the rub is. This is where the debate is in the literature. Because if anybody says, well, look, the second law means that you've really got a system which is always going to run down, you're not actually going to get things to increase in complexity, to increase in ordered machinery, able to do more and more useful things, then they say, well, we don't live in the world in an isolated system. The technical term would be our biosphere, which means the world and the atmosphere around it, is receiving energy from the sun. It's sometimes even receiving projectiles from outer space. So it clearly isn't a closed and certainly isn't an isolated system. So they then say, well, we can then produce machines, we can produce useful energy to do work just by bringing in energy from the sun or from some other nearby star. And that, they say, will eventually produce some useful work in order to make machines over millions of years. Now, is that proposal correct? Do we get nice ordered energy? By ordered energy, I mean energy able to do work, energy able to make machines, right? Do we get that over millions of years of lots of energy coming in from the sun? Well, actually, intuitively, most of you know that this is, we're on shaky ground here, something's wrong. But actually, this is argued for seriously in the literature. And that's what was being said on a famous radio program, where it was said to me, there's loads of energy out there. But that was a very wrong scientific comment, and I'm going to show you why. Is that true scientifically? It isn't. It's wrong. Let me show you why. Machines, I've already said, are devices which have raised free energy. Let me use an analogy. I've got a spring here. I'm going to come forward and I'm going to wrap it around this little pole here. But now, if I do this, if I move this over to one direction, right? This spring wants to move into equilibrium. So it doesn't naturally want to stay in that state. Now, if I say to you that molecules in all living systems are in a raised free energy state, then I'm using this spring like an analogy. The molecular bonds are actually a bit like a spring. This is a mechanical device, but it's actually to do with chemistry. And the chemical energy is in a raised free energy state. The DNA has lots of bonds which are in a raised free energy state. The proteins in your body are all in a raised free energy state. Actually, it's obvious, because if you take meat, which is protein, out of the fridge, what happens after a few days? Wretched smell, pong, which makes you want to throw it away because that stuff is decaying. The bonds are going to equilibrium. It doesn't want to be in a raised free energy state. It may take a little while, but it will decay and the smell will come with it. Okay, you with me? So it's obvious. Most of us realize this. But when we put it in technical terms, it sometimes goes over our heads when these people who are making these points using the technical terms, we may miss the implication of what they're saying. But they're trying to argue that energy coming in from outside will somehow raise the energy states of the molecules, somehow reverse the process that I've just been saying. No, it won't, not unless I've got some intelligent system involved to make that happen. So this is what I'm putting technically on the screen here. Like I was showing you with that spring, the free energy is ready to be released. Most molecules are in that state that they want to go to equilibrium. And a machine is a device which has locally raised free energy or ordered energy. When I had this spring like this, right, when I actually when I moved things in that way, that was ready to do work as soon as I released it. And actually, living systems are full of molecules ready to do work as soon as they're told to. Go and do this, go and do the other. That's what's happening all the way through the cells in our bodies. So, to set the spring, like I've just been doing, requires initial input of ordered energy, which was my hand in that case. Very crudely done, but it makes the point. Now I'm going to try and make this point using another illustration. Again, please note this is an analogy. It's really biochemical energy which is going on in living systems. But let me use an illustration. I loved to play with magnets when I was young, didn't you, some of you? You loved to get the iron filings and see all the patterns made by the magnet from underneath, you know, and we suddenly realised, oh, there's things like magnetic fields. There's north and south poles. Well, look, if I've got a north pole here, which is the red, and I've got a south pole here, which is blue, when I put these together, wham, they come together. I can feel them pulling, right? Now, what would happen if I take a north pole to a north pole? It doesn't want to come together. I have to really sort of make it. Look, you really are going to come together. And finally, I get it to come together, right? And I'm pushing it. I can feel the force that I'm having to put in to make it come together. But as soon as I let go, it wants to pull apart. See? So I have to put in precise, ordered energy to make this become a useful device to do something, boing, when it's told to. That's what I'm getting at here. And a machine is a device which has raised free energy. So what I'm now going to show you is another example, right? This is not a wind turbine, even though it looks like one. It's a nice little toy, but it makes a good point, which is this. this is a solar-powered turbine. Now, if I have lots of energy coming in from the sun, right, and I don't, in other words, have a machine able to capture and transfer the random energy from the sun to useful energy to make the turbine go round, will anything happen? Nothing's happening, is it? Now, supposing I put that there for 1 billion years. We've got a long way. But how about a multiverse? Maybe that would be the answer. Supposing there might just be a universe out there which would do this if we just get enough universes, you know, like 10 million. Maybe one of them would do some funny things with the laws of thermodynamics. You know full well that just ain't true. So, number one, you can't appeal to time. And number two, you can't appeal to the multiplicity of universes. The laws of thermodynamics are universal. That is, as Dembski rightly said, there's no such thing as a free lunch. That's basically what the issue is. You can't reverse the laws of thermodynamics. Now, let's be clear here. Those who are not on our side will immediately say, as I've been repeatedly acknowledging, but you've got an open system. You're not really talking about the second law. That's true. They are correct, because the second law only applies to an isolated system. I'll just explain the technical terms so that people who are watching this know that I'm aware of this, that an open system is where you've got matter and energy able to come through the boundary. A closed system is where it's closed to material coming in, but it's still open to energy, and that's technically what we've got here. We've got energy able to come in. And an isolated system is where you've got you can't get energy in, and you can't get matter in. So technically what I've got here is a closed system, but it's a non-isolated system. And the point is, that's not going to help you. A non-isolated system argument is not going to help. It's only when I take my thumb off the solar cell and I enable the energy coming in to actually be captured. You see what's going on? It's being captured by this remarkable machine, and I'm using the strict definition here, that converts the energy coming in into useful energy, which will drive, in this case, a turbine. And of course, that could then be used to make electricity, which could then feed your hairdryer or whatever it is you're going to use it for, the cooker and all the rest of it, okay? That's basically an energy conversion system. And it's converting from random energy into useful energy. And it's raising the free energy locally, enabling it to do work. The vital point is that you need a machine in order to raise the free energy. So even though this might seem a complicated point, actually when you think about it, it's an obvious point. These things are not going to happen without an intelligence involved. Some of you get ridiculous presents at Christmas in your crackers, don't you? And one year we got these. We had great fun. I think we had grandchildren with us, and we were winding these up and putting them across the Christmas meal table, right? And this is a chap which walks across the table, and you have to wind him up, and you have to put energy in, but you have to put energy in not randomly. I don't just shine it on the sun, you know, hoping this will wind up. I actually have to wind it up properly, and I have to put the energy in, and then it does something useful as it races across the table. Stupid things, but, you know, makes the point, doesn't it? And here's another example. This is just an electric motor, which might keep me cool in the summer, you know, and that you find them at service stations as you go down. Rather nice, isn't it? The ladies like them. And perhaps the fellas do as well. I don't want to be sexist. But, you know, you've got a battery in here, and the battery is no good unless it's going through an electric motor, and the electric motor raises the free energy locally to make the turbine go round. It's all the same point. This is a machine, and that's the basic point I'm making. Oh, thank you. It's still talking to me. So we have here, well, that's the end of my wind turbine. So we have here a most important issue, that wind turbines, and in particular the one that I'm using, which is a solar-powered turbine, don't actually do what they're doing unless there is a machinery available, which means intelligence, in order to make this machine work. So it's not a matter of having the energy. You've actually got to have the solar cell, you've got to have the machine there in order to raise the energy locally, the free energy locally. Now, let me just introduce you to a gentleman who actually said this years ago. I'm not the first to have said this. This has been said by very thoughtful, deep-thinking scientists in the past. And one of the ones that a number of us have a great respect for, he's died now, is Professor Wilder Smith.
There are exceptions, and these exceptions confuse. If you take, say, something dead, like a stick, that formerly was growing and using the sun's energy to increase its order, but it's now dead. Now, if I expose that stick to sunlight in an open system, this stick will get warm. In fact, it's quite warm now because the sun is quite strong. Now, that means that its organization is decreasing. Its entropy is increasing. Now, that's in an open system. Why doesn't its organization increase? It should do, according to the law of evolution, the postulates of evolution. If I take, on the other hand, not a dead stick, but something that's living, like this nice little orchid here, early spotted orchid, that orchid is absorbing sun's energy just as this stick is absorbing the sun's energy. But the energy that falls on that from the sun is, by coupled reactions, being used to increase the order and to grow. The chlorophyll does that. But if I kill this orchid, if I would pick it and let it die, the energy of the sun would fall on it, and then it would get hotter and therefore more disorganized. What's the difference then between the stick, which is dead, and the orchid, which is alive? The difference is that the orchid has active, what the scientists call, teleonomy in it. It's a machine which is capturing energy to increase order. This machine is dead and is not capturing energy to reduce disorder and to increase order. There's the difference. Where did the teleonomy come from? The teleonomy, the ordering principle, does not reside in matter itself, but it does reside in life. And where you have life, you have teleonomy, and then the sun's energy can be taken and make the thing grow, that is, increase its order.
That was brilliantly put by Professor Wilder Smith, and it makes that point, I think, very ably, that you cannot just produce machinery just by shining energy on to something. All it does, it just heats it up. The energy from the sun, of course, shines on leaves, which are an example, as I said earlier, of machinery, because the energy from the sun is absorbed, but in a very particular way. It's absorbed such that the carbon dioxide and the water in the air and the carbon dioxide, is then coupled together with the energy from the sunlight because of the photosynthesis machine on the surface of the leaf, and it produces sugar and oxygen. Now, this wouldn't happen unless you've got the photosynthesis equipment there first. It's basically just like a solar cell. Not exactly like it, but it's a similar principle. It's actually locally raising the free energy in order to do something useful, to make sugar, which the plant needs, and oxygen, which is actually very useful for the rest of us who breathe it. So you need machinery. Energy on its own would not raise the free energy. So we need to recognize the vital importance here of machinery. And this leads us really to a thermodynamic principle for non-isolated systems. I hesitate to call it a law because obviously you've got to have everybody agreeing before you call it a law. But I would suggest to you that there is a principle which has been missed in the academic literature. Let me propose what this principle is. In a non-isolated system, the free energy potential will never be greater than the total of that which was already initially in the isolated system, so there could have been machines already there, and that coming in through the boundary. Right? So, yes, there could be some free energy available doing some useful work. There could be some machines already in the system. But you're not going to build any more than what was there to begin with just by shining random energy through the boundary. And it is important to understand that free energy has a specific definition, meaning that energy which is available to do work. And technically, for those of you who do read some of the literature, it is the overall enthalpy, the energy available totally, minus the entropy times temperature to get the units right. So loosely, the free energy is the organized energy in the system. It's a bit like what Wilder Smith was saying, the organizing principle in the system. Or sometimes I've used the term machine. It's the free energy device. So free energy, organized energy, machinery, it's all the same point that's being made here. So when we had that proposal earlier, what's the answer? Is that scientific? The answer is, of course, that ain't scientific. It's wrong. Empirically, that is, doing experiments to see what happens in the universe around us, everything is telling us this just ain't true. It does not happen. And random energy does not build machinery. So, the principle that I'm suggesting that we should acknowledge, we perhaps won't call it a law because we would need a number of people to agree this, but I would propose this principle that the free energy potential is never greater than the total of that which was there already, plus that coming in through the boundary. And that coming in through the boundary must mean that there is a transcendent reality which is able to build machinery, or at least convey how to build machines. And everything's telling us that it's not going to happen just by natural processes. Let's now look at molecular machines. In the cell, in the nucleus of the cell, there is a very important little town hall, as it were. And in the town hall, the center part of the cell is chromosomes and DNA in particular, which is like a bank of instructions, coded instructions, which are referred to constantly by all the other machines which are in the cell, which need to refer to that digital bank of information to actually work out what to do next. Actually, everything happens so fast that you have millions of processes going on per second in every cell of the human body and all living systems. One of them, which is very important, is the ATP motor, which is the motor which converts inorganic phosphate and adenosine diphosphate into a raised energy molecule called adenosine triphosphate. The ingredients come in, which will be food of some kind, and it's really to do with the respiration of the cell. So the energy comes in, and the ingredients come in, and they're converted to ATP. There is a proton gradient going across a membrane, which drives this, what is effectively an electric motor, because it's driven by this proton gradient, hydrogen plus gradient here, and it converts the ingredients into a raised free energy molecule. This is most important because without ATP, you wouldn't be able to build DNA, which is absolutely essential for the storage of information. Which leads me now to this important issue concerning the formation of DNA. DNA, deoxyribonucleic acid, discovered by Crick and Watson in 1953, is formed as a polymer. And these blue strands are the double helix here. There's two sides to it. And they are sugar phosphates, as it says here, sugar phosphate backbone. Then going across the double helix, you have what we call base pairs or nucleotides. And they are formed from adenine, which will link to its opposite pair on the other side, thymine, and guanine, which will link to its opposite pair, cytosine, on the other side. So G will go with C, and A will go with T. Now, the message-bearing side of DNA will actually have a string of these nucleotide base pairs, which will code for making particular amino acids. But I just want to refer to this point, which is what's called cellular respiration. Technical term for basically processing or harvesting energy stored in food. In other words, cells, in order to make their DNA, actually need energy to do it. So this is telling us how to get that energy. And it's called cellular respiration. It's the process by which cells get the energy in order to make all the stuff that they need to do. One of them is to make DNA, because you need to constantly form new cells with new DNA in the nucleus. And the other thing, of course, is to make the proteins, which are made of amino acids, which actually does involve the coding stream of the DNA. I'm particularly homing in on the making of DNA, because this is something that most people don't realize. They like to think that if you had the sugar phosphate in a Petri dish, and if you had the guanine and the adenine and the thymine and the cytosine, that they'll all just come together, you know, and everything will be hunky-dory. No, it won't. And I'm not here referring to coding issues just at this point. I'm coming to that. I'm not referring to the ordering principle, but I will come to it. I'm just simply talking about how do you get the sugar phosphates to come together to put what we call polymerize DNA, to make this long string on the outside of DNA. This is before we start putting on all the nucleotides in, right? How do we make that sugar phosphate backbone? How do you do it? Will it just form in the Petri dish? The answer is no. Because this is where ATP comes in. Now this gets complicated. But I don't apologize for the complication, because the phrase is often used, the devil is in the detail. Well, I'm going to come to a different conclusion. And then actually, it's the fingerprint of God is in the detail. There is a mind even involved in the thermodynamics of the formation of DNA. And I haven't even yet got to the information system, which is the nucleotides. Just look at this rather complicated molecule. It's called deoxythymidine triphosphate. It's a triphosphate. Please note that. Don't worry too much about the detail here. Those who can understand the detail can see it on the screen. But I want you to just note that it's a triphosphate. It's 3 phosphates. So what we've got here is that this is the base pair, which will become involved in the nucleotides. But this is the phosphate, right? And this is the sugar. So we've got a sugar phosphate, but we've actually got 2 other phosphates added onto it. And why am I stressing that? Well, you've got the thymine, which is the nucleotide, or will become part of the nucleotide base pairs. You've got the sugar, and this phosphate is in a triphosphate mode. That's unstable. Doesn't want to stay like that. It wants to come down to a monophosphate. It wants to lose those 2. But it's important that it is in a triphosphate mode for the following reason. All those phosphates will not come together unless they're in a triphosphate mode. So the thymine needs to be attached to a triphosphate molecule. The adenine has to be in a triphosphate mode or attached to a triphosphate. And so is the guanine, and so is the cytosine. All of them, if they're going to actually form the DNA, they have to be in a triphosphate. In other words, they have to be in a raised energy state. Now, those who do A-level chemistry, those who do degree level chemistry will know that this is to do with activated bonding. It's to do with things being in an activated energy before the chemistry will take place. These are the actual building blocks of DNA. This is the nucleotides, guanine, adenine, cytosine, and thymine. And of course, there's two types, which we know of the nucleotides. We're not so much stressing the nucleotides here. What we're stressing is the sugar phosphate attachments. So each of the guanine and the adenine, the cytosine and the thymine are all attached to a phosphate. When it's actually all polymerized, it's a monophosphate. But when it's in the business of beginning to polymerize, it has to be in a triphosphate mode. Right? This is the point. So if we're going to string, in this case, it's thymine, guanine, cytosine, and adenine. But if we're going to make this backbone of the sugar phosphate, which is absolutely important in DNA, and then we have, of course, on the other side, this would be the coding string, this would be the non-coding string of the double helix, then it will attach, of course, A going to T, C going to G, and so on, and A going to T down there. And the DNA, we know, zips and unzips, zips and unzips. It's constantly going on as lots of machinery comes to the nucleus, the town hall, to actually pick up the information and go and do whatever they're going to do, which is to make the appropriate proteins which are made of amino acids, which are coded for by the TGC, or maybe coded by another triplet of the nucleotides. But I'm homing in on how do you actually get that sugar phosphate backbone to polymerize to begin with. And the answer is that you have to bring up the ATP. Here it is. It's in a raised energy state. It gives off energy, and it raises the energy locally, both of the thymine and it may be of the guanine and all the other nucleotides with their phosphates. So the monophosphates have to be loaded with energy to make them into a triphosphate, and then they will bond. That's the issue. So in this particular case, we've got adenine, thymine, thymine, but it could be any one of those triplets which we want to form with the sugar phosphate backbone around it. The similar point will apply to the monophosphate for the cytosine, the monophosphate for the thymine, and the monophosphate for the guanine. Each must be activated to a triphosphate before it polymerizes. Now, I know that's complicated, and I don't apologize for it. But what I want you to grasp is one main point. You've got to put energy in a very special way before the backbone of DNA will join up. That is the issue. And these all have very special names for their monophosphates, but it has to be made into a triphosphate, which is the red symbols here, before they will do it. So, summarizing, you've got some energy level, and you want to go to a raised energy level. In other words, DNA is not in equilibrium. That is the issue. Remember, I had this point about the mechanical slinky, that I said that I'm in a raised free energy state there. Well, that's what I'm saying biochemically with the DNA. The DNA phosphate bonds are in a raised free energy state. How am I going to go from there to there? I can't do it just by shining lots of energy on it. So that point about there being lots of energy out there to do it is wrong, because I've actually got to have an ordered system to raise the energy locally. How does DNA do it? Well, it does it with ATP. You cannot get to the finish, because that is what we call an endothermic reaction. It requires energy being put in a very specific way. And systems won't do that naturally. They'll normally go the other way. They'll go exothermic. So if you start with something which is in a raised free energy state, it will lose its energy, and we call that an exothermic reaction. What's the answer? Well, as I've been hinting at all the way through, we've got to go to a raised energy state, and that's what the ATP does. It says, here chaps, I'm available, I can put in the energy, And then you could relax back to your polymerized state in a monophosphate bond. And we call that an activation energy. Chemists know about this. Those of us who are working in chemistry and combustion also know about it. Biologists, if they studied carefully these molecular reactions in biochemistry and living systems, they know that there is an activation issue here. The raw building blocks in the Petri dish will not just form DNA. That will not happen. The free energy change is going uphill. You can't do it. You've got to have an ordered energy input. So you raise, first of all, the building blocks to an energized building block, which are all ready to go, ready to do what they're meant to do, which is to relax back and form the DNA monophosphate backbone. So that's where ATP comes in and says, here chaps, I'm available. I'm going to raise you up to a free energy state. And then it relaxes back from that to DNA where the free energy change is negative. Now this all makes sense. You've got to have a tool there. It's like saying, I cannot build something unless I've got a spanner. It's saying that there must be that specific tool available, and that is DNA. That will work. But now, here comes the fly in the ointment. The ATP itself is a very unstable molecule. It's never found outside living cells. The ATP itself needs a very highly organized chemical pathway for it to be made. And yet DNA cannot be formed without it. So you've got big problems. If you're going to say all this came about naturally, you've really got a whole host, not just one, but a whole host of chicken and egg situations where one thing is depending on another all the way through. It's a system. The whole nucleus is a system which requires a master plan, a master engineering blueprint to make everything fit with one another. So we know that monophosphates won't make the DNA. It cannot happen. Triphosphates, though, will make it happen through the intermediate ATP. Now, if you thought that wasn't enough, there is something further. And this is where we begin to move to the issue of information. Let me just remind you, ATP does not form spontaneously. It is formed by a very endothermic reaction itself. You have to put energy in. It is easily reversed and unstable. It is produced by cellular respiration itself. Right? The ATP, as I showed you earlier, it's produced by careful bringing in of energy in a specific way in order to make it. It needs organized structures of the cell in place and very specialist catalysts, which we call enzymes, in order to make ATP. It is manufactured by enzyme catalyzed reactions in a highly regulated chemical environment. So you've got uphill thermodynamics. That's really what I'm trying to argue here. And that doesn't happen naturally. Well, if you thought that was you, as I say, there's something even worse coming. If you thought that that was complicated, now let's look at the connection with information. Your head hurts, yes. I know it hurts. Bound to hurt. Because we're dealing here with detail, but that saying the devil is in the detail is actually that the mind behind the universe is in the detail. And that's what we need to realize here. If you want to look at this more, you can look at my paper, which is available on the internet from that web address, and it's called Information and Entropy, Top-Down or Bottom-Up Development in Living Systems. And it's in the International Journal of Design and Nature and Ecodynamics. When you download it from that website, you can get all the detail behind what I'm saying here. We need to ask the question, what defines information? Information is somewhere in this system. Everybody knows that. Everybody will accept that. Is it in the DNA molecule? Is it in the DNA code? Is it in the energy stored in the molecules? Is it in the DNA polymerase, which produces DNA? Is it in the nucleotide bonds or the nucleotide themselves, which go across the double helix of DNA? And we could ask a number of questions here as to where the information lies. Now, the materialists, the reductionists, the people who are well known for adopting a reductionist principle, have to ask themselves the question, where is the information in these systems? This picture is very graphic, and it really demonstrates something very important here, because people try to argue that information is increased if you have mutations in the system. Not necessarily, to be fair to them, will they say they're not saying that all mutations will cause an increase. They accept that most mutations are deleterious, like polydactylism here. But Richard Dawkins definitely argues in his book, A Devil's Chaplain, that mutations are what actually increases the information base, and that some mutations will be advantageous. Now let's examine that thesis, because Kimura, who's a Japanese geneticist, produced some years ago this distribution where he showed that the frequency of mutations plotted against mutation effect is, as we'd expect, generally very high for deleterious ones, particularly as you come to those which don't really have a huge effect on us, as we call it phenotypically. That means the organism level. But as you come out here, there are some which still have an effect on us, even though they're smaller. They do have some effect, and they do come into the population. Things like spina bifida, colour blindness, cystic fibrosis, the Down syndrome, haemophilia. All these are serious genetic diseases. Let me just come back to this bit in the middle, because you'll see that there is an admission here that there might be some positively beneficial mutations. We need to explain this box in the middle. It's called the neutral box, and as I said or hinted at earlier, at the genetic level, just the odd mutation can be carried. It doesn't actually affect us on the phenotypic level. That's the organism level. That which affects us on the organism level is outside this neutral box. And as you can see, nobody's ever found beneficial mutations which clearly are not just an advantage, just the odd advantageous mutation, but you need a whole string of them before they will actually affect us at the organism level and produce wings in the right place for a reptile, such that it's also got the muscles available to actually fly. A classic case where this has been attempted in experiments in the laboratory is irradiating fruit flies, these tiny little fruit flies, where if you've got fruit lying around, you begin to see them buzzing about. And these tiny fruit flies have been irradiated, and what has happened is that on occasions you do get mutations where you get wings coming out where there should be eyes. But do you get the muscles with them so that they will work properly? No, of course you don't. In other words, you get a mutation which might appear to be an advantage, but it's not actually going to affect the phenotype level. That is, it's not going to affect the organism level. Actually, it's a great disadvantage, really, because without those muscles, it really comes over here, and it will die out anyway. So mutations are generally deleterious. John Sanford, in his book Genetic Entropy and the Mystery of the Genome, actually discusses this issue and makes the point that we're gradually suffering more and more genetic diseases in the human population. So are mutations the answer? No, they're not. That's not where the information lies. Remember I had this picture earlier that we know intuitively, and now I've given you the rigid argument, or the rigor to make this argument more clear to us and to give it a much sounder base. That information requires specific sequencing. That you can see that information is not just to do with random signals. It's to do with a signal which is carrying a specific sequence. which is understood by the emitter and the receiver. You see, GCC in the DNA code stands for an amino acid, and it's understood by the DNA. Understood is the wrong term to use because there's no mind there, but there is a recognition that the DNA, GCC, stands for saying, go and make a particular amino acid for which GCC is the code for it. And CAT will mean go and find another amino acid, link them together, and begin to make the string of amino acids which forms a protein. And it's the same way for us with English, or whatever language you're familiar with, that you have a sentence here which means something, both to that which is making the signal and that which is receiving it. And that which is receiving it in DNA, of course, is the RNA, which is the single-stranded version of DNA which comes along and takes the information from the town hall, the DNA, and it goes away, and the ribosome actually makes that particular amino acid come along and attaches it to make the protein. Codes are important. Supposing I've got this statement, there are 10 kinds of people. You say, well, go on, what are you trying to say? Well, supposing I then went to say, those who read binary and those who don't. Are you beginning to get what I'm saying? 10 in binary means 2. It doesn't, you thought it meant 10 to do with the base 10. But if you have a base 2 counting, then that sentence makes sense. There are 2 kinds of people, those who read binary and those who don't. But initially, it wasn't making sense. But as soon as you realize, he means in binary, then it means something, and the sentence makes sense. It's just a joke, but it makes a point that actually coding is important. The symbols don't make their own code. The code is not actually formed by the symbols themselves, and it certainly isn't formed by the matter. Information requires specific sequencing and an agreed code between sender and receiver. So, my conclusion here is that information is non-material. So, the evolutionary perspective is the one on the left in this picture. The idea that matter and energy, millions of years ago, gradually formed a simple information sending and receiving system. Many people have tried to argue for an RNA world, where you don't have double-stranded DNA, which they recognize as unstable, but actually neither is RNA very stable either, right? But they try and argue for it, and they talk about abiogenesis. Nobody's ever resolved it, and they never will, because actually it's impossible to form that system, because you're actually trying to make the thermodynamics go uphill, as I've already shown you. The sugar phosphate bonds won't come together in RNA, let alone DNA, on their own. You actually need machines to do it. So abiogenesis won't work. And then they try to say that, having glossed over the fact that it won't work, they then try and say that the nucleotides ordered themselves to start making a message. But messages don't come without a mind, without an intelligence behind them. And so they now make this fatal jump that information is somehow arising out of matter without any intelligence. And everything is telling you that that doesn't happen. And then they argue that complex systems then invented the idea that we are intelligent, and people invented the idea that there is a God behind the universe. And they actually seriously talk about the evolution of religious concepts. May I say that actually this is utter foolishness. I shouldn't have to do talks like this. I shouldn't have to go into the science of every little stage and show to people that scientific law after scientific law is being broken by such foolish viewpoints. But I have to, because colleagues in universities are seriously writing papers and proposing and deluding people who are their students, into thinking that the science has somehow proved that there is no intelligence behind the universe. It is evident that a child can understand, really, the right-hand column, that there is a mind and intelligence which designs things like computers. You may not have thought that there was really a big company called Microsoft, which does sometimes get it right. I know sometimes we feel like kicking out computers, but, you know, that Bill Gates and his merry men actually have designed information systems, which actually are a very poor copy of the wonderful, effectively, software systems which are going on in DNA. Indeed, many people are now copying DNA and using DNA to make even much more sophisticated computers today. But the point is here that mind is needed and intelligence to make those information systems full of software. Now, what person in his right mind would say that software arises by accident? As I've said, you may feel sometimes that Windows 7 or Windows 8 is something which arose by accident because it's full of errors which constantly need correcting. But actually we know that that just doesn't happen. Machines do not arise by accident, and software doesn't arise by accident. Now, the interesting point is that when you reverse this picture, now you get a sense of understanding, which only comes from looking at the evidence this way round. If you say that there is a mind which put the software there, and if you then say that the software is effectively an expression of the whole system which has been designed, which is now causing the nucleotides to be ordered in a particular way because it's an expression of a message, and that message is now forcing certain molecules to be in a rage-free energy state, all in a system, in an ordered way, such that when they release their energy, everything begins to do what it's meant to do, and do it perfectly well, thank you. Then you begin to realize that that's the only way to understand living systems. That it is the software which is controlling the thermodynamics, not the reverse. It's not the thermodynamics which is somehow making software. It's software, information, which is non-material, which is controlling the thermodynamics. Now that is what I'm appealing for in the universities of our Western world, and indeed across the whole world, to actually begin to look at the biochemistry from a completely different perspective. Then we begin to understand what's going on. Werner Gitt is another excellent scientist who's put so much original thought into this whole issue. He wrote the famous book, In the Beginning Was Information, which is well worth reading. And he makes a number of points. He actually talks about 5 levels of information, but for the sake of argument, I will just discuss 2 levels. If you've got a CD, then the CD or DVD is not going to weigh any more when it's got information on or when it hasn't. It's not going to weigh any different. In other words, information isn't defined by matter. It's not the amount of matter here that defines information. What about the energy level? Well, the laser, which is actually used to read this disc, will have the same energy level in the reflected beam as when it had information, when it didn't have information, when it has information. What's going to be different? It's just simply the rearrangement of the light is going to be different when it's got information, and that's recognized by the receiver. So language and code transcends material. And the message, and this is a second point, could be written in a number of languages. In DNA, it's written in DNA code, and the message transcends the language and the code. That is just something which people have not grasped in our universities. That message is something which is transcendent to matter and energy, and even to code. And the code, the language, is certainly transcendent to matter and energy. So that question about what defines information is probably best understood by making an analogy with something which I will show in a moment. The conclusion I'm saying is that information is the message expressed by the instructions and software, a product of an intelligent agent. Well, if you say that in most of our universities today, people don't want to know, because it obviously has philosophical implications. There is intelligence. This is the analogy that we're going to use. You see, everything is telling you that there is a fingerprint of intelligence. Let's now use an analogy. Supposing I don't ask the questions of DNA, but I ask the questions of music. Where does the information lie in Chopin's Nocturne in E-flat major? Where did it come from? Is it the strings of the piano, the keys, the ink, the acoustics of our ears, the pianist? Or is it somewhere else? You see, we're playing here a beautiful piece of music by Chopin, but we're asking the question, where does the music come from? Obviously, we all know it comes from Chopin. If we leave Chopin out of this, you've lost the plot. If you try and say that the music made itself, you are in a pretty sorry understanding of music. I know you might think that some music makes itself, but most good music is actually got a mind to it and an intelligent conveying of beautiful structure. Where does that structure come from? It came from the mind of this wonderful composer whose statue still sits in the middle of a park in the middle of Warsaw, and he brilliantly probably wrote down this music to make sure that it didn't escape him before he got it down in a state that it could be passed on to other people. And this lovely piece conveys to generations following the beauty of what was in his mind that lovely day in Warsaw. Now we might say the same thing of DNA. Where does the information lie? Where is the information? Well, of course the information is from the product of a mind. Well, whose mind is it? It's obviously the mind of God himself. And please notice I'm arguing here that the evidence shows us that the mind is transcendent. There's no basis here for pantheism. It is a transcendent mind, a mind which is above the universe, which has made it. And of course that is entirely consistent with the Bible. I will admit that there are other possibilities. We've obviously got other religions which do speak about a transcendent mind. But the obvious one, which is consistent with this, is the Christian message, which says in the opening verse of John's Gospel, in the beginning was the Word, which in Greek is logos. In the beginning was the logical principle behind everything. And it's not just a principle. I tell you, my dear friends, it's a person. The person who not only formed everything, the exquisite DNA in every one of our bodies, and the distant galaxies which the Bible says are sustained by the word of his power. All these were made by the eternal Son of God. And I'd like to ask you at the end of this talk, have you grasped that not only is he the creator, but this book goes on to say that this world which has become broken by sin is actually going to be redeemed by, first of all, you being redeemed. You need to be redeemed. And the greatest thing that Creator did was by coming to this world to die on a cross, to be our Saviour. May God bless you all. Thank you.